Hello, welcome back for part 2. This is on the particle nature of electromagnetic radiation. In 1900 to 1910, Max Planck and Albert Einstein proposed that light was a stream of particles called photons, and the energy, the E of those photons, was equal to h times frequency. Where h is a constant called Planck's constant. And so the equation that we use to talk about the energy of a photon is that E is equal to h times frequency. And since we can, by our equation from our previous video, where we can say that C is equal to frequency times wavelength, we can algebraically manipulate this equation to say that frequency is equal to c over wavelength, c being the speed of light. And c, if I didn't mention it in the last video, c as the speed of light is a constant, and it's going to be 3 times 10 to the 8th meters per second. 3 times 10 to the 8th meters per second. So that's what you'll always use for the C value in this equation. All right, so we can say that the energy is equal to h, Planck's constant, times c, the speed of light, divided by the wavelength. And Planck's constant is this, 6.626 times 10 to the negative 34th joule seconds. And then when you go through and you do your calculations and you can see how the units cancel out, we see that our unit is our final unit is in joules. So here's an example. So let's say that the energy of a photon, how do we calculate the energy of a photon in, let's say, a sodium vapor lamp? The lamps that you see on the highways are sodium vapor lamps, and it's an intense yellow-orange colored lamp, and the wavelength of that light is 589 nanometers. So let's calculate the energy. So the energy would be equal to Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds, times c, which would just be the speed of light. And then I would divide that by the wavelength. This here, 589, is the wavelength. And I would just have to make sure that I do that conversion from nanometers to meters. So whenever you're doing your calculation with these equations, whether it's this equation that you're using here or this equation that you're using here, your unit of wavelength must always be in meters because of the unit of C, which is meter per second, and because of the unit of Planck's constant, which is joule times second. So so you plug in your two constants as your numerator. Your denominator simply is the wavelength in meters, and you get the amount of energy per photon. So then let's say we want to calculate the energy of a mole of these photons. Well, if the answer that you got from above is the joule per photon, and we know that there's 6.02 times 10 to the 23rd photons per 1 mole, because remember that Avogadro's number of 6.02 times 10 to the 23rd is a counting unit. And if we're asking for the quantity of a mole to get an actual number, we would just say that number of photons per mole. And then you multiply it out and you see that photon cancels with photon here, and you end up with the joule per mole here. Okay, so it would be, that's the quantity that I'm trying to calculate. So you could include that as well, the joule per mole. So then we're going to take this one step further, and we're going to say, so what if the optic nerve needs 2 times 10 to the negative 17th joules to send an impulse to the brain? How many photons are needed? So then what we know is that that's the quantity of energy that we know we need. And we know from calculation A that there's 3.37 times 10 to the negative 19th joules for every photon. I would then use that as my conversion factor here. And I want to set it up this way so I can see that joule will cancel with joule, and I'll end up with 59 photons. I'm going to stop there.